Welcome to the Chapter 36 review for sensors. Today we're going to talk about Chapter 36 on page 383, control strategies. And as I said in my earlier discussions, the focus for reading this chapter is to not get bogged down in any of the math. The focus here is to understand some of the core concepts and look at them and read about them and try to see if you can understand how the concept works and not get crazy on the math. So the first thing we need to do is talk about a control strategy. A control strategy is how some sort of either manual or automated system uses inputs to determine how it's going to control things or determine the output. So a typical control strategy is an on-off control strategy. That means the CV, the control variable, is either on or off. All right. And in a heating system like your house, that's a very typical on-off control strategy. The idea is when you're asking for heat, your heating system turns on and it warms up your house until it rises above the temperature your thermostat says, whoops, now I got to shut off the heat. Then your heat shuts off and it cools down the whole house. So you're constantly heating up or cooling down. You're never maintaining an exact temperature. There's some furnaces, electrical furnaces, that use the same strategy, but instead of just being always on and then waiting for the temperature drop and then being always off, they can do on-off sequencing to kind of pulse. So the more pulses of energy applied to the electric heating system, the more energy goes into your oven, and then the oven can maintain its temperature a little bit better than a pure on-off system. So that's a slightly different thing. But when we say on-off control, we're talking about the kind of heating system that your house uses, either heating or air conditioning. And on the top of page 384, there's a great illustration of what happens in terms of your actual room temperature over time. It's always going up, hitting a high point, going down, hitting a low point, up and down, depending on whether or not your heating system is on or off. So your heating system just goes on, off, on, off. And that's what this little square wave is trying to show, that when it's hit the top of the square wave, it's on. When it's at the bottom, it's off. And I guess they're talking about an air conditioning circuit here, not a heating circuit. So they've given you some notes about how that works. Now, let's talk about what's happening next. Next, starting here on the page 384 at the bottom, we start getting into a different kind of control. We're outside the range of on-off. Now your control variable, we assume you can adjust your control variable a little at a time. So I have the ability to do proportional control. So the more my error changes, the difference between my set point and my target, and my actual red, the CV, my red temperature, for instance, that is proportional to control. So the more the difference is, the more I open up my control valve. That's proportional. So in proportion to my error, I can increase my heat. And we talk about how proportional control works. And in that realm, we talk about gain. Gain is this number we apply to our error to determine our control output. So gain is simply the number we use to multiply by the error to give my output statement. Gain is not something I ever have to worry about. Gain is usually calculated by my control system. So don't worry about all this math here. Read about it, learn what these formulas are, but you never have to use these formulas. Okay? We also have the possibility, instead of using a simple gain, we can use something called proportional band. And they're not really in use much, but they are a range of input values that corresponds to a full range of output from a controller. So instead of using a simple number to figure out the change in control output, I use a set of values that's specific to my process output control range. So I've got an input range and I've got an output range, and those two ranges can be used to calculate internally, which you'll never have to do in reality, how that control valve will be set. So we also have something called output bias. And then you can read the definition here. That's a very important definition. Let me highlight these guys. Proportional band, it's output bias. So these are all different control characteristics. Once again, you will never have to do the math in the real world. And so output bias. The next key value is offset. Sometimes I have a minimum valve opening I want to always maintain. So that minimum distance, like percent open of that valve, might be an offset of 10%. So I always want to maintain on my output a certain offset. It can also be related to the process variable. So offset, it might be a number that you set as a parameter in your controller. If you always want to have it running 50% open minimum, you might set an offset of 50%. All right, so that's another, and they go through how we use the offset and proportional band. That's a useful little thing here. And then they also talk about how open loop response diagram. Don't worry about that, skip that. It's a useful little term, but open loops means there's no effective feedback. So the next level of variable control, having an analog output for your control circuit, is integral control. So it's a method of changing the output of a controller by an amount of proportional error and the duration of that error. So they're using a math function, not only how long, basically not only how big the error is and how far off temperature you are, but the longer you maintain that error, the more your automatic formula calculates your integral control level. So if I've been off temperature for 5 minutes, right? My temperature might be a simple gain. But then if I've been off temperature for 20 minutes, then that gain increases. So each period of time that you're off temperature, you add to the change in your controlled variable. So it will keep cracking open that heat until it sees a response to your temperature. So it's looking at the speed of change, not just the amount of error, but the speed in which you're responding to your changes in your control temperature. It, once again, is a calculation that's done inside these controllers. You'll never have to do this calculation yourself. But the integral control is the speed. And it talks about how that works. It's useful, but not great. Integral helps you respond better to rapidly changing situations. It helps you respond better to a big change in the load on your control system. That's what you have to remember. It's an excellent change in load characteristic. Then the third level of control is called derivative control. Derivative control wraps up this control mechanism called PID. This sounds familiar to P and ID, which is piping and instrumentation diagram, but PID stands for proportional integral derivative. It is a classic method of controlling process systems. It is a great, great method. And it allows for you to get very, very accurate control. And frankly, most modern controllers do PID loops automatically. You don't have to do anything about it. You don't even have to set these parameters yourself. It will be auto tuning. And so the little cheap controller that we used in class is an auto tuning controller, and it doesn't need anybody to set these parameters. It does it for you. The book talks about these parameters just to give you guys a background on how this control works. Derivative control is great for giving you a very accurate target in terms of set point versus actual control level. So you can read about how the derivative control works. It's a method of changing to the output of a controller in proportion to the rate of change. So that way, the faster your temperature changes, the greater the derivative effect is on the control mechanism. For instance, if I drop a huge chunk of cold chocolate into my vat in my chocolate factory example, that rapid change in temperature to the rest of the chocolate will trigger more of a calculation inside the computer there to say, whoa, I better rapidly open up that valve and get a whole lot of heat into that tank to make sure that we can get back up the temperature quickly. So it's looking at the rate of change. And there's a lot of math. We have a little fun factors here. I'm not going to highlight this, it's not that important, and how that actually works. There are a few other concepts of control, such as feed-forward control. Read about it. It's interesting. I've never actually used it in any systems I've installed, but it's useful to learn. We also have various other concepts, such as cascade control, radio control, and in the last few, I'm not even going to go through the advanced control strategies here. AI is becoming more common out there. The idea that we can use some sort of advanced tool like R. R is a software tool to do AI kind of work, and fuzzy logic. Read about them. They're interesting, but really, to be honest, I don't expect that you'll see them in anything in the next 10 years. And neural networks, the same thing. These are all really advanced concepts and not important, as far as I'm concerned, in the real world today.